Hello, everyone. Welcome to this new session of the Gamma Seminar. Our speaker today, Javier de Lucas, now in Montreal, but normally in Warsaw, is going to talk about k-symplectic Lie systems. So, Javi, the stage is yours.
Okay, thank you, Xavi. So, last week we have the general theory about k-symplectic structures. So, I decided that since many of you are worked on these systems, and there are 13 structures that appear in many works we are sharing, okay, I could talk about k-symplectic systems as a mixture of, as an application of k-symplectic geometry, and also as a way to find new results on k-symplectic geometry. Many of the things I will explain today, they can be extended to all the types of Lie systems. Okay, so pretty much you can copy and paste what I am going to do. And normally, the only thing I recommend is that if you are going to use this idea for other structures, is always to add some new idea, because by itself, okay, it can be interesting, but I would recommend to find something else apart from the application. I mean, yes, for example, doing K-Poisson Lie systems, okay, can be done, but one always has to find some reason, some good reason to do so. So, let us start. This works. Now, I will introduce Lie system. I have done it several times, but anyhow, let me just recall the main things about it for those who don't remember, or just to explain a couple of details. Then after that, I will introduce Lie systems with compatible k-symplectic structures. This is a little bit weird from the point of view that normally k-symplectic structures, as Xavi said a week ago, are mainly used to study field equations. So when you try to transform them to study ordinary differential equations, because maybe as you already remember, these systems are systems of ordinary differential equations of a particular type. The thing is, sometimes, well, most times, you have to change the formalism used for field theory, and sometimes you have to change it in a non-trivial way. The way, for example, the way of defining Hamiltonian vector fields for just a one vector field for a k-symplectic structure, it's a little bit more complicated. And also, certain things that you used to do when you have a Hamiltonian k-vector field with respect to a k-symplectic structure, the things you used to do in that case are a little bit different from what you are going to do to apply these formalism to ordinary differential equations. The formalism, it has to be adapted. And normally this way of adapting it, it's not given in a unique way. It can be done in several ways. So one has to pick up the proper way, or one of the proper ways to do so. And normally the way to find how to do this modification of the k-symplectic formalism is just looking for applications, or looking for appropriate mathematical properties in the formalism. So this is going to be the third part of the talk. And I will do this application of k-symplectic structures in such a way that you will have some hints of how to do the same for the other differential structures. I mean, for example, for k-contact, for k-poly Poisson, and other ones. Okay, for at least to have some rough idea of how it should be done. So let me recall you that Lie system is a system of first order ordinary differential equations. Its general solution can be written as a function of a finite number of particular solutions and 13 constants. I'll consider 13 constants. Okay, so this is the normal thing you do when everyone is studying his degree on mathematics or physics during his first year, and one studies, for example, first-order systems of linear differential equations, the matrix differential equation, yeah, with constant coefficient. They will notice that the general solution is a linear combination of a finite number of particular solutions with some coefficient that can be, well, anything, yeah. And the system, the family of particular solutions are such that they are the initial conditions at certain time they are linearly independent. So you can think of Lie systems like a generalization, non linear generalization of this idea. Okay, the general solution could be a function, not necessarily linear, of a finite number of particular solutions. And you will have 13 parameters which will allow you to describe each particular solution of the general system. Okay, so where these Lie systems appear, well, there are thousands. Well, thousand maybe is too much. Well, yeah, there are thousands of applications, surely speaking. Well, there are lots. Let us say it this way. So you have this Svartian equation. They're all related to the Svartian derivative. For example, this is one of the things. There are Buchtal equations, relativity, spin system, viral models. Really, there are lots of things. I have been looking for applications in many fields. Okay, in general, almost all systems of differential equations cannot be described by means of Lie systems, but that doesn't change the fact that we have lots of potential applications in control theory and partial differential equations. Also, you can find these Lie systems. You can find them in the financial models. You can find them in the mechanics. You can find them everywhere. Okay, you have really lots of them. It's not the general stuff. It's not easy to find them, but anyhow, there are good reference where you can find many applications and you can find inspiration to find even more. So this is from the point of view of applications. Mathematically, the structure related to Lie system are normally compatible with many geometric structures. Okay, for example, with contact structures that it was done with Xavier and I will do it. Yeah, with Riemannian structures that this was done with Mariusz Tobolski and with Ranz, Francisco Jose Ranz. With supermanifolds, this was done by Winterneath, okay, a long time ago. And truly speaking, there are just a few works about it, and there is much space to keep on doing things. And Lie system with multisymplectic structures were studied, well, maybe it was with Silvia Vilariño, Narciso Román Roy, Xavier Gracia, Miguel Muñoz, Xavi also. Rivas, yeah, and now I don't remember if I'm missing someone, but essentially with them. And there are lots. I mean, every geometric structure is compatible with Lie system, can be made compatible. And I am most sure I have not a theorem to tell you, but I am most sure that almost every geometric structure can be made compatible with Lie systems in a way I will explain now, a similar way to what I will explain today. And there are always a lot of applications. Say, I have no theorem, I cannot be sure, but I have done this so many times that the only difference from one structure to another is that to make them compatible, it can be a little bit more difficult or easier, or it can happen that the number of applications is bigger or smaller, but there is always field to apply this. Okay, there's lots of things you can do. So in this talk, I will focus on study Lie system through k-symplectic manifolds. Indeed, this was published, what I'm going to tell you, Journal Differential Equations. This is one of the very best journals in the world about differential equations. So just to tell you a couple of comments, this topic is very interesting, okay, for many reasons. So you can quite well apply this to interesting topics and to find some interest. Okay, so the thing is that the main thing about this is that normally, as I said, k-symplectic structures are used to study, were described to study field equations. I mean, system of partial differential equations, but here I will focus on system of ordinary differential equations. So, as I said, we really have to change many things about the formalism, the k-symplectic formalism, but the spirit is pretty much the same. So let us recall superposition rules and the systems by means of the standard example. I mean, the Riccati equation, this thing. It is usually said that this is the simplest non-trivial example of a Lie system. So on the real line, okay, x belongs to R. You have a first order differential equation like this. In normal form, that means that the first derivative on the left-hand side can be written as a function of the time, I mean the independent variable and the dependent variable x, okay, where b1, b2, b3 are time-dependent functions, and they are all arbitrary, okay? And it turns out that this Riccati equation satisfies that its general solution can be written as a certain function of three particular solutions, like it is written in here. This particular solution at O values x1, x2, x3, and some constant k. And you see, when you fix three particular solutions, that they must be different, okay? If you can say that if the three particular solutions are the same, this generates nothing. I mean, because this will be 0, this will be 0, and this will be 0, this will be 0, and this even will not have much chance, okay, eventually. So the thing is that if they are different, and k can be any constant, by changing k from three particular solutions, you will generate different solutions of Riccati equation, okay? So why is this important? This is interesting and important because normally for B1, B2, B3 arbitrary time-dependent functions, you don't know which is the solution of this thing, okay? You are not sure, okay? And even if you can get the general solution, it can be difficult to describe the general properties of the general solution. But you know, even if you can get three particular solutions, for example, by means of numerical methods, you can work out an approximation of the general solution. And there are lots of things you can do with this expression. For example, there is Flocky theory that studies these equations and other of the sort with time-dependent periodic parameters, time-dependent parameters. And one of the things that it is important is to determine the number of solutions with periodic orbits and things of the sort. So, you know, if you have three particular solutions, you know the number of periodic orbits, you will be able to describe if the general solution or all particular solutions of this equation, they will have periodic orbits. This is an example, okay? So this expression that is known, it's been known for a long time, can be written more geometrically in this way by saying that the general solution is a function, okay, a certain function with dependence of 4 parameters, depending such that if the first parameter is substituted by a particular solution of Riccati equation, the second by another one, and the third by another one, and the 4 parameters is a constant, you will generate the general solution by inserting this thing. So this is what is called a superposition rule. And the important thing about this is that even when this system of differential equation normal for this Riccati equation is time dependent, coefficient depend on time, you see that the superposition rule does not. Okay, so in a general way, a superposition rule for a system of first order ordinary differential equation on n in normal form, I mean, like before, is a function, okay, which depends on m times the manifold. This will be used to take into account the dependence of the superposition rule of the particular solution and particular solutions times n, with here this parameter will be used to generate up, when you fix n particular solutions, all the solutions of your equation. You know, if you have a differential equation, first order differential equation on a manifold n, okay, for every point of n, you can associate always a particular initial condition of the manifold and generate the particular solution related to it. So if you want to describe all, you will need as many parameters as points of the manifold. So this is the thing. And the general solution can be written in this way in terms of M generic particular solution and a constant. What does it mean generic? Who knows? I mean, every example is different. Okay, for Riccati equation, they must be different. For linear systems of differential equations with constant coefficients, no, they must be linearly independent. This is something different, but normally the set of particular solutions, the initial conditions that can be used, is normally something that it is tense in this space of This is the only thing it happens. In this case, a 13 parameter. So the definition is the typical one. The system is a system of first-order differential equations admitting a superposition rule. This is quite clear. I mean, most systems of differential equations, most differential equations, though do not admit a superposition rule, but it turns out that many of the differential equations that appear in physics do have. And that's, for example, what happens when you are studying analysis of your first year of studies in mathematics or physics. Okay, so the thing is that these systems had to be described, they had to be characterized, and the characterization of these systems was due to Lee. Okay, to see how this goes, I will recall you that when you have a Riccati equation, associated with this Riccati equation, you can write a time-dependent vector field. And a time-dependent vector field is nothing but a family of vector fields parameterized by a t parameter. You see, here what you have for every t is a vector field, and that's all. Essentially, you can do it geometrically very nicely, but essentially this is the thing. So the thing is that when you have this time-dependent vector field associated to this differential equation, okay, the thing is that you can decompose this vector field as a linear combination in this way. You have a b1t function multiplied by x1, b2t function multiplied by second vector field, and b3t function multiplied by a free vector field. And these free vector fields satisfy that when you work out the Lie bracket of this vector field, okay, you see the bracket of the first and the second. The first with the third that gives twice the second and the third gives the third. So these things, these commutators, they close a Lie algebra of vector fields, and this constants that here that describes the commutator of vector fields as a linear combination of a basis of this Lie algebra of this thing are called constant structures of the Lie algebra. It can be proved that this is isomorphic to SL2R. And what Lie said in 1880 was that if you have finite-dimensional Lie algebra vector fields on the real line, well, he said that the analytic Lie algebra vector field, everyone is locally diffeomorphic to this Lie algebra or to a sub-Lie algebra. So essentially, on the real line, you don't have more possibilities. Every Lie algebra is at a generic point. This is what also said by Lie. Diffeomorphic, there is a change of variables that maps it into this form. Yeah, so this is the most important list on the real line. Essentially, it's the only one at almost every point. There are most cases, okay? This is something that I'm writing now that it's at a certain sense, it changed a result that it has been set for, 140 years. So it's quite interesting that there are many more cases, okay? This is what I will publish in a couple of weeks. So let us continue and let us write this more formally, okay? And the thing is, when you have a system of differential equations in normal form, non-autonomous because depends of time, you will attach these to a third time-dependent vector field, to this one. You see, for x coordinate xi, you have these functions, and these functions will be the components of a time-dependent vector field, okay? On Rn, where you have your system written this way. It is said that the system X, because this expression tells you that when you have a system, non-autonomous system of first order differential equation normal form, this is this, you can attach it to a time-dependent vector field, and you can do it the other way around. When you have a time-dependent vector field, you can write a certain system of differential equations in a unique way. So you can identify both things, and the Lie system theory, what you have is that systems of non-autonomous differential equation normal form, they are described by means of time-dependent vector field. Geometrically, is nicer. In practice, is nothing. Okay, it's exactly the same. So everything is, for now, will be rather described by means of time-dependent vector fields, remembering that a time-dependent vector field is a system first-order differential equations on normal form that is non-autonomous. So the Lie-Seffer's theorem is a theorem that characterizes Lie systems. So a system X, I mean the system of first-order differential equations in normal form, non-autonomous related to the time-dependent vector field admits a superposition rule if and only if it can be written in this way as a linear combination with time-dependent functions or a certain basis of vector fields spanning a certain finite-dimensional algebra of vector fields. The Lie algebra is called normally a Bessel-Gulper Lie algebra. Okay, and the main proposition due to Lie is that all the Lie systems on the real line are at a generic point, locally diffeomorphic, I mean up to a change of variables, are kind of Riccati equations. So essentially it's that. There are more details, but this is enough. So I will show you now one example that is important to many of us because you have been studying these as similar things. And this is called the Kummer-Schwarz equation, or the Schwarz equation. Okay, this is something of this sort. This is equation number one. The thing is that you can see that if you consider the A is the differential of B, B is the differential of X, here what you have is indeed a third-order differential equation. Okay, if you substitute A like a second-order differential of X and B like a first-order, this expression you obtain by substituting this thing is a third-order differential equation. And it turns out that this third-order differential equation describes something called the Schwarz derivative that is very important to describe hypergeometric functions, to describe field models, string theory, integrability of mechanical systems, lots of things. Okay, so the fun thing was that I discovered during my PhD that if you this Schwarzian equation, the real Schwarz equation, this whole third-order differential equation, you write it in this manner, it turns out that this is a Lie system. Okay, this is kind of so because you have a certain third-order differential equation related to sandwich problems, and it turns out that it satisfies this very strong condition. How did I find it? Okay, I found it because I noticed that there is a relation between this equation and all the ones that were Riccati equations. Okay, Lie systems, sorry. And they have 30 properties. For example, the Schwarzian derivative for homographic transformation is 0. Okay, so I noticed that this can be used to create a superposition rule, and this was the final hit. I know that it can be done. So the thing is, if you write this, you will notice that the right-hand side can be written, okay, as a time-dependent vector field that will be a linear combination of this vector field, y1, y2, y3. And these three ones, when you pick up the commutator of these vector fields, it turns out that you obtain a Lie algebra isomorphic to SL2R. The fun thing is that it looks like a lot like a Riccati equation. This is the first thing. The second thing is that this is real. The real Schwarz equation is complex. So if you want to do this for the real Schwarz derivative in the general case, you will have to do this in a complex manner. This is something that it's not be done, okay? And some of you are doing. Okay. And also, this is related to many structures you can study, and it has important applications. So it's an interesting example that can be used in many ways. So the thing is that in k-symplectic theory, this system is related to a certain nice structure. So take a look to something. You don't know why, okay? I will tell you that I did this magically. I mean, I found the first time I wrote this, it was because I just noticed that it can be done. Don't ask me why. Okay, because I don't really know how I obtained it. Yes, I wrote it. And I found these two things. This thing here is a closed form. If you pick up the differential of this, it will be 0. And this one that is very well known for people in the University of Warsaw because it appears to find out potential and monopole, Dirac monopoles and things like that, is also closed. So the fun thing is that these both differential two forms are closed. Okay, and there is another fun thing, and is that if you make the contraction of this differential form with the vector fields of the Poisson-coalgebra algebra of the Commerce equation, it turns out that all these vector fields satisfy something like the property in symplectic geometry. The contraction of omega-1 with the first vector field is the differential function. The contraction of omega-1 with the second vector field is the differential another function. The contraction of omega-1 with the third vector field is the differential another function. And you can do exactly the same with the second symplectic form. Symplectic, sorry, it's not symplectic, closed form, omega-2. These two forms are not symplectic because they have kernel, both of them. Indeed, this first one, the kernel is the partial in terms of x, okay? And in here, I don't remember now exactly which is it. I should work it out, okay? But it has also kernel. Indeed, is a differential two form in a three-dimensional manifold. And the image of these forms are always even dimensional, and the kernel is the annihilator of the image. So in this case, the image will be two-dimensional, the annihilator will be one-dimensional, so there is annihilator, and this is the kernel of this. So this form has a one-dimensional kernel, this form has a one-dimensional kernel, but it happens that the intersection of these kernels is 0. And this means that this thing and this thing, these two forms, that they are close, but they are degenerate because they have kernel. They said that they are presymplectic forms, and the intersection is equal to 0 is something that you saw last week. This is a two-symplectic structure, okay? It turns out that we have construct a two-symplectic structure, and this two-symplectic structure is such that every vector field of our Poisson-coalgebra algebra, with respect to every form of this thing, okay, it becomes Hamiltonian. But, you know, there is something interesting, because here, when you have this two-symplectic structure, these two closed form with whose intersection of kernels is equal to 0, every vector field of our Poisson-coalgebra algebra is linked to a one Hamiltonian function, one for its presymplectic form of the case, or in this case, two-symplectic structure. So the thing is that when you have what we will call a Hamiltonian vector field relative to k-symplectic structure, this vector field, they will have a so-called k-Hamiltonian function. It's not the thing we did last week that Xavi did last week. It's a little bit different. In field theory, in k-symplectic, we have k-vector fields, we have k-symplectic forms, and we can contract to obtain one Hamiltonian function. Here is something the other way around. You have a k-symplectic form, you have just vector fields, just simple vector fields, and related to them, you will have k-functions. Okay, so it's a little bit different. It's not difficult, but its different properties are quite different from what you expect at the beginning. So you see, all these formalities has to be changed. So yes, to fix things, sorry for the notation, because at every work is a little bit different. Xavi said, and people are very ready to annoy themselves to make anyone else to use their own definitions, but just say that a k-symplectic structure nowadays is a symplectic structure on a manifold in which the dimension of the manifold is fixed, okay, it's proportional to k plus 1, and you have these forms in such a way that all of them, they are close, okay, and they are pre-symplectic in the sense that they are close, and the intersection of all the kernels is equal to 0. Okay. So when you have these k forms, you can gather them all together to form what is called a k polysymplectic form. It's nothing that a differential form taking values in Rk in such a way that the components of this differential form are just the components of the k-symplectic structure. Okay, so the thing is that you write this thing. They are little weird but acceptable cases. You could, for example, consider that one of these forms is symplectic and all of the remaining ones is equal to 0. So this is a perfect case because, you know, when one of these forms is symplectic, its kernel is going to be 0, and the other one, well, they are close because they are 0, no problem. So now, the definition that fits our intentions, what we wrote before, is that this is a k-symplectic manifold, and we said that a vector field is k-Hamiltonian if y is Hamiltonian relative to each form of the k-symplectic manifold. I mean, the contraction of every pre-symplectic form with y is the differential of certain function. Okay, so now the natural definition that one can use: a system X is a k-symplectic system if it admits a Poisson-coalgebra algebra of k-Hamiltonian vector fields with respect to a k-symplectic structure. This is what we did with the Kummer equation. Yeah, we have two pre-symplectic forms. We have a three-dimensional Poisson-coalgebra algebra, and every element of the Lie algebra was Hamiltonian with respect with each one of the pre-symplectic forms of the k-symplectic structure, two-symplectic structure. Yeah. And in that case, everything was right with the dimension that it had to be fixed. But it is a type of this with here, because in Kummer-Schwarz equation, the manifold is three-dimensional. The k is equal to 2 because we had two symplectic forms. So we have 2 plus 1, 3 times 1 is equal to 3. That is the dimension of the manifold we were studying. Okay, so there is something interesting about this, and it links to a question made by Oscar a week ago. And the thing is that the concept of k-Hamiltonian vector field was indeed defined during the origins of the k-symplectic theory. The k-symplectic theory was mainly developed at the beginning by Awan, by Gunther, by Manuel de Leon, by use another name. Okay, so but they were more or less equivalent. Okay, more or less, I mean that there are several issues about how to define and about dimension of the manifold, about the pre-symplectic structure and so on, but more or less they were doing more or less the same. And the thing is, also what I said about these Hamiltonian vector fields with respect to a k-symplectic structure is a little bit weird now. The thing is that it was defined at the very beginning by, I think that it was Awan. And why it wasn't developed? Because no one knew what to do with it, essentially. They had no idea how to, they were thinking about field equations. And vector fields, standard vector fields, they are not much appropriate to study PDEs, to study field equation, partial differential equations. So they forgot about it. It was said, they tried to do certain things, but they noticed that they can not be done because the usual stuff with symplectic geometry cannot be generalized to these vector fields. I mean, in symplectic geometry, you have brackets of functions, and you have a Poisson structure induced by them. You have certain properties with it. But here you remember that a vector field, a Hamiltonian vector field relative to a k-symplectic structure, has k functions. I mean, every k-Hamiltonian function is just a function which taking values Rk. So essentially, for every Hamiltonian vector field relative to a k-symplectic structure, you will have k functions. So there was no way, no rational way, no good way to make a bracket with that. And absolutely was not a Poisson one. So people didn't know how to deal with it. Okay. So this is the thing. Okay. So imagine that you have a polysymplectic form. Remember, you have a k-symplectic structure. You have this is a basis of elements of Rk. The coefficients are the forms that give rise to a k-symplectic structure. Yeah, so they are presymplectic, and the intersection of the kernel is equal to 0. And remember that when you have a Hamiltonian vector field, this vector field is Hamiltonian with respect to every presymplectic structure. So if you contract the forms omega y by this vector field, you will obtain k functions. So you will define something that is a function taking values in Rk, whose components are indeed each one of the functions, okay, that you obtain contracting the vector field with every of the forms. And this is one of the things you have to take into account, is that you have different functions for this Hamiltonian vector field, but every function related to every presymplectic form is related to the same Hamiltonian vector field, only one, okay? And the thing is that if you have 13 functions that satisfy this, the vector field will be unique, because if they were two, the difference between them contracted with the omega e would be 0. So the difference of these two Hamiltonian vector fields, okay, would belong to the intersection of the kernels of the omega I. And you already know by the definition of a k-symplectic structure that the intersection of that kernel is 0. So once you have the functions, these vector fields uniquely defined. Okay, if you have these vector fields, functions are not uniquely defined because you can always add some constant to hi, and this condition is satisfied. Now, when you have a Hamiltonian vector field, as I said, this structure, this thing that gathers together all the Hamiltonian functions of your Hamiltonian vector field relative to a k-symplectic polysymplectic form, okay, this is called an omega Hamiltonian function. Okay, and C omega, C infinite omega is the space of all these omega Hamiltonian functions. So you see, in the example we had at the beginning, you have y1 that with respect to omega 1 had this function, this Hamiltonian function, and related to omega 2, it had this Hamiltonian function. So you pick up the first function as the first component, the second function as the second, and this h1 is an omega Hamiltonian function for I1. I2 the same, we will have this thing. I3 is the same, you will have this thing. And you have to take into account that how the hell we can do now a Poisson bracket or Lie bracket with this function, because normally, you remember, in symplectic geometry, when you have two functions, you define a Poisson bracket in such a way that the Poisson bracket of these two functions should be the Hamiltonian function of the Lie bracket of this vector field and this. So the question is, could we do such a thing in here? Is there any way of defining this? The answer is yes, it can be done, is here. And the way of doing that is that if you have some C omega, C infinite omega Hamiltonian functions in this way, the omega bracket is just to make the bracket of each component and make the tensor product with I. So it works, this at this bracket, okay? And in the case of the Kummer's bars, the question when it happens is that for H1, H2, this bracket gives that H1, H3 gives you 2H2, H2, H3, like H3. So this is a very nice way of dealing with many, many components, because recall that each vector field, x1, x2, x3, sorry, y1, y2, y3, had different Hamiltonian functions, but anyhow, this allows you to construct some bracket that it will be worked in a nice way to deal with all the coordinates at the same time. So in there is analogy in k-symplectic geometry that comes from symplectic geometry and says that you have this exact sequence, okay? And the only thing I would like to tell you is that there is a way of describing Poisson algebras. This is very important, for example, for applying the Poisson-coalgebra method of Ballesteros, Herranz, and Ragnisco, and all these people. Okay, and it's a way of describing k-symplectic geometry by means of a certain Poisson bracket. The thing is that this bracket in here can be proved that it is not a Poisson bracket. Essentially, the problem is that if you multiply two functions in here, okay, like in the Poisson bracket, the product of two functions, the coordinates, will not be an omega function. Okay, because it will happen that the new function does not need to be related to the same Hamiltonian vector field for each component. So there is no multiplication, standard multiplication of omega Hamiltonian functions. There is no such a thing. It's not well defined. Okay? If you have an omega Hamiltonian function, it's related to a Hamiltonian vector field, the second two. But if you multiply component by component these Hamiltonian functions, it turns out that it may happen that this is not an omega function for a certain Hamiltonian vector field. So it does not work. So since there is no product of functions, there is no Poisson bracket, there is nothing. But there is a trick. And the trick is if you compose this polysymplectic structure with an element dual to RK, okay? I mean, what you do is just to make a linear combination of every omega E, okay, the omega E you have, this gives you a Poisson bracket that is called the theta bracket, okay? Every vector field of omega vector field will have an omega function and a Hamiltonian function relative to it that is given by the contraction with theta, and this will be a Poisson bracket. And you can do a lot of stuff with this structure. Okay, and now for Kummer-Schwarz's equation, okay, the time-dependent vector field, as I told you, was described by means of a linear combination of the vector field y free, the time-dependent function b2t times the y1 vector field, and it turned out that y free is the vector field related to a Hamiltonian function, or omega Hamiltonian function h free, this one h1, and it turns out that for each t, this thing is a Hamiltonian function relative to our omega Hamiltonian structure for this time-dependent vector field for this t. And it turns out this function, as I saw before, they close a Lie algebra. So this thing can be understood for each time as an element of this Lie algebra of omega Hamiltonian functions. So this thing is like a curve in this omega Hamiltonian omega Lie algebra. Okay. And this curve is called a Lie Hamiltonian structure. This is what in here. So if you have a manifold, you have a polysymplectic structure, and you have a certain time-dependent omega Hamiltonian function, you say that this is a Lie Hamiltonian structure. If this thing for each t, these elements, this omega Hamiltonian function, with respect to this bracket, they can be contained in a finite-dimensional Lie algebra. Okay, and if it's done so, you will prove that if you match every ht with its associated Hamiltonian vector field, as I told you, this is unique. Well, this means just convention. This will be a Lie system. So by means of this thing, you will have a Lie system, and the other way around related to a k-symplectic structure. And the other way around, it also works. If you have a k-symplectic Lie system, you will have a Lie Hamiltonian structure of this type. So what I am going to show you now, this is Kummer-Buzz's equation. No, this no. Since I'm running out of time, okay, I will show you something that I did lately with my colleagues, the son of you. And it's not ideal, okay, but it works very well in many cases. So let us go back to this Kummer-Buzz equation, but please take into account the details. Here, Z, B, and A, they are complex numbers, but the time here is real, okay? Take this into account because different versions of here are by assuming that the variables are complex, the time are complex, the functions are different times. Here, Z, V, and I, they are complex. This B or T is any complex function, whatever you want. And the parameter T is real, okay? So this is related to the Spartian derivative, a Spartian derivative that appears in certain problems, okay? Where Z is complex and T is real. The real Sparse derivative is such that this T is not real. It's an element on a Riemann sphere. Here is real. It has applications, but not all of them. So when you write this fun thing like a complex system in real one to write it down, it turns out that it is a Lie system and is described by means of a time-dependent vector field of this sort. And this thing BR is the real part of the B function, BI is the complex part of the function. And now, instead of having three vector fields closing as SL2R manifold, what you obtain is a family of 6 vector fields closing a Lie algebra doing the structure, the concept of structure that is isomorphic to the complexification of SL2. Okay, so and you ask me, okay, fine. What are you going to do with this? Okay, what I'm going to tell you is that the important thing, because this is used many times with this, and it's a key to use a lot of structures to describe the systems, okay? And it's the following thing. One important thing about these vector fields is that they are at every point linearly independent. At each point, if you pick up the value of this vector field at this point, the second, the third, and the sixth, at each point, they are linearly dependent. They span the total tangent space to the manifold where it's defined. The manifold is 6-dimensional, and they all span at every point the tangent space. Systems of this type are called locally automorphic Lie system. I will not explain why it's related to Lie groups, but the thing is that. So what's the fun thing? The fun thing is that there is a miracle. For these locally automorphic Lie systems, if you have a Lie algebra that is isomorphic to whatever, Lie algebra, vector fields, you will have another Lie algebra of vector fields that commute with every single one vector field I want. And there are no more. I mean, for these vector fields, every vector field on our manifold that commutes with all of them is a linear combination of these 6 ones. Okay, they all commute. You can ask me, how the hell could you obtain this expression? Well, some of you know. I just sat down and I work them out. This is an option. And in most of the cases, I do that along with many tricks. And I managed to write it. Okay, I have done it many times, so I have many tricks to do so. And the funny thing is that this Lie algebra is exactly the same as before. Okay. And it turns out that the Lie algebra of Y1, Y6 was such described that it has exactly the same structure constant of x1, x6. I mean, this means that if x1 and x2 is x2, for example, the Lie bracket of Y1 with Y2 will be also Y2. This is the same way of commuting. And now imagine you have these vector fields. They are locally independent at each point also. It can be proved. So since they span the tangent space, you can work out some differential one-fourths that they are dual to them. They are uniquely defined, okay? And the thing is, these differential one-fourths are pretty much useful to describe the system. Normally, you are used to use coordinates and to describe differential force in terms of a base or differential of the coordinates. Okay, that thing is absolutely unuseful in certain problems. The thing is that these differential waveforms, they have pretty nice properties, okay? And that's why we use them. First, due to the way that they commute with these vector fields, and these are dual to these things, to these symmetries, it turns out that the Lie bracket of these differential forms with this is equal to 0. They are invariant. So they are differential forms that they are invariant with respect to these vector fields. And there is another nice thing that is quite shocking at the beginning, is that if you work out the differential of these differential forms, the differential of this will be a linear combination with constants of these forms. Indeed, you have this. Differential form first is minus the fifth stereo of the sixth minus the 1 stereo of the fourth, an expression of this sort. Even if I had some time, I could tell you that this constant in here and the terms that they appear, they are used to the constant of a structure of the algebra. You have the constant structure, you automatically can write down these expressions. So this is a very nice way to control what is the differential of this. And you can see that this thing, for example, is closed, because if you pick up the differential again of this, it will be equal to 0. But this is very nice, because remember that to construct k-symplectic structure, we need differential two forms, and the kernel, they must be closed, and the intersection of the kernels must be equal to 0. So you see, if you pick up this one and this second, you will immediately see that the kernel of this one, since this is eta 1, eta 4, eta 5, eta 6, will be y2 and y3, because they are dual to this, and this. So you immediately see which is the kernel of this, and you know that it is closed. And as I said, the kernel of this is 2, 3. The kernel of this is 1, 6. So since the kernel of this and the kernel of this has no intersection, this thing is a polysymplectic form. You can do with this, with this. There are many, many ways, and they are most of them quite trivial. And these forms, this differential for the coefficients by construction, since they are the differential of these invariant forms, the Lie derivative of this eta 1, eta 2, eta 4, for example, is 0 with respect with our vector fields x1, x6, it turns out that that guarantees that this vector field are Hamiltonian. So it turns out that this method told you that we can construct a k-symplectic structure quite easily using the structure, the constant structure of the Lie algebra, and turning a certain Lie system into a Hamiltonian one relative to a k-symplectic structure. And this, my dear, is an idea that works so well that it can be used in maybe much to say, but I have been using this idea for many years, and there are full of applications related to full of systems. So I recommend you to use it for many other cases, because you will notice that it is important. This idea is done roughly, I mean, by means of cohomology or Lie algebras and Lie algebra methods. One could find all the k-symplectic structures, could characterize when these k-symplectic structures is and this, and all this stuff. The thing is, no one did it. No one knows how to do it, and it's an open problem. It's an algebraic one related to Lie groups and Lie algebras. So this is something that can be done. It can be applied to many cases, and I think that it is a good moment to finish. Thank you very much for your attention. I hope that this was worth your time. Thank you.
Thank you, Javi, for your nice talk. Are there any questions or comments?
I hope that, yeah.
I have a question here with the 6y vector fields and 6x vector fields. So for instance, if we take X vector fields, so it's like the three of them are symmetries.
Yep.
And the three other are related to the Lie system, right? Because it's an automorphic Lie system. Yes. And okay, so we have SL2 plus SL2 from the six of those. Yep. And the Y's are from the complexification, right?
The Y's reality is because they are symmetries. I mean, what it happens in here with these vector fields, okay? There's one you had in here. The thing is, how to explain it?
Okay, so which one are, like if we considered the non-complexified case, we would have that, for instance, x1, x2, x3 are the Lie system vector fields.
Yeah, and you could have y1, y2, y3 symmetries.
Oh, okay.
And the y1, y2, y3, indeed, if you work it out, and these are the infinitesimal transformations of Moebius transformations.
Right.
And in this case, these six I got here, if on the complex, I mean, this is the third order jet, let us say, of a complex of a Riemann sphere. And what it happens is that you have on the Riemann sphere homographies, okay? And you can extend homographies to this third order jet, okay? And the infinitesimal transformations induced by these could be the Y's, okay? In the non-complex case, it will be y1, y2, y3 are the infinitesimal transformations of the lift to the third order jet of the Backlund, of the Moebius transformations. In here you have six, okay? And this is because you have more complex transformations, okay, Moebius transformations on C, okay? And what you do is that every such transformation can be lifted to the space of jets, yeah, and gives you a Lie group action. And this Lie group action, since you have complex Moebius transformations, you will have in their 6 parameters, because the coefficients of the Moebius transformations, they have 6 degrees of freedom. So what you have in here are the infinitesimal transformations of that. This is quite, I mean, this example has a lot of geometry. I could talk about an hour about this example, okay? And the thing is, these vector fields can be described of a jet manifold, and the symmetries are the extensions to the third jet manifold of Moebius transformation of the Riemann sphere. That's why I obtained this. I did the way of working it. This is Moebius transformation of the Riemann sphere. You push it up to the third order jet to work out the infinitesimal generators, and these things commute with this. Okay, so this is the thing. If you do it complex as you are doing, Temon, okay, here you have free vector fields on the third order jet, essentially. Yeah. So you pick up Moebius transformations on the Riemann sphere and you extend it to the third order jet. So you will have free symmetries, complex. Since they are complex, they generate a complex Lie algebra. Yeah, it's L2C, yeah, the complexification. Yes. And here you will have free vector fields Y and free duals. Free, only that the duals will be complex. Yeah. And you will have only 3 of these. 1, 2, 3. Okay, yes. I don't remember exactly which one will be, but they can be done. You will have 3. And I'm pretty much sure that taking both of them, you will have a k-symplectic structure. This is one of the things. If you pick up 3 of them, the resultant system will be multisymplectic. Okay, so the example you got is probably that you have 3 of these, you put them together, and you will have a free differential form. It would be invariant, and this would be something for complex Kumer-Bats equation. But you know, here this D is that in the complex case would be, you have different options. You have the total D, you have the two doubles differential. With each one, you will have exactly the same. So you will have many options.
Okay, thank you.
And you can do this in your work. I mean, it's new. It's not that, but it's clear how to do it, more or less, I think.
I will.
Okay,
Thank you.
Javi, maybe you could explain how to obtain these relations 3, 4, and 5, relating the etas with the differential of the etas, because probably there's some people who don't know how to do this, and for sure it's not computing the etas and then the differential.
No.
Checking everything. You can explain the trick, because
yes, sure.
It can look like black magic to some people. So.
Indeed, normally this is the usual stuff one does for students in the first or the second year. I mean, you have the trick to do it, and you know the result is nice, but the students don't know the trick, so they do the calculations. And it's fucking difficult, if you allow me to say that, for them to work out. They have to learn how to calculate, and it's very easy to check where they were wrong and if the final result is property. So the trick is, well, I don't have my pen now to show you, but the trick is when you have this eta here, okay, eta 1, what you need in here are the structure constant of the Lie algebra. Okay, so you see you have here this one, this one. What are going to see is for the vector fields, the duals to the etas, let us check where we have on the right hand side y1. Okay, and when you see this is I4, no, I5, no, I1, oh, I want one of these. Okay, when you have this, you have that the first and the fourth vector fields, when you work out the Lie bracket, you obtain the y1. So what you do is in here you add a term with the eta 1, eta 4 with a minus. Minus is because you have to add a minus to the number you obtain. Now you have here still eta 5, eta 6. So how it comes? But if you keep on looking for y1 on the right-hand side, 0, this is y2, y3, y5, y3, y2, you finish here, and you obtain y5, y6. So if you go here, you pick up eta 5, eta 6. The 1 is the number appears in y1 on the right-hand side, you add a minus. So differential eta minus is equal to this. If you do it with eta 2, you do exactly the same. Look for places where you have E2. For example, you have in here, so you have a 2, 4, and you have in here, you have a 3, 5. But you have to take account that this is a minus. Yeah. So you will have 4, 2, yeah, because it was the minus, it was 2, 4, and a 3, 5. And for 3, you will have a 4, 3, a 3, 2, and so on and so on. So these expressions, they are very easy to obtain. And there is just one remark. If you pick up this eta 1, eta 2, eta 3, eta 4, eta 5, eta 6, if eta 1, you do the tensorial product with an element of Rk, these two things, these all together, they can be called a 1-4 Maurer-Cartan form. And the differential of this Maurer-Cartan form by means of these things that they are on the right-hand side give you what is called the Maurer-Cartan equations. So this expression in here is the expression in coordinates of something that is very well known for Lie groups. So know the Maurer-Cartan form and its properties, you can work out this. So, you know, here, this example is truly full of geometry related to Lie groups, cohomology of Lie algebras, and different geometric structures. So to do this properly, to find it, you need to know a lot about differential geometry of very different things, and you have to put it all together. But once you do it once, you can pretty much use it for the other examples. Is it clear maybe now? Or
Yeah, I think now it's more clear. Because otherwise
well, it seems to be magic, but it's not magic. This
yeah,
when
it's not.
in differential geometry you obtain such a nice expressions, something must be happen. I mean, it's not a question.
Yeah, but I suppose that some people didn't know the trick, so
No,
probably
I
it
guess.
helped. Probably it helped more than one or two.
Yeah, and many of you will have at one moment or another to use it. So I think it is worth the time. Okay.
Okay. Any more questions or comments? No? Okay, so I guess we can stop here. Thank you very much, Javi, for your nice talk.
Thank you.
And see you all in a week.
See you. You can stop the recording.
Yes.